We're now going to look at question 4 from the 2022 A-Level Further Statistics paper. In this question, we are told that in a game, a spinner is spun repeatedly. And when a spin is spun, the probability of it landing on blue is 0.11. We are asked to find the probability of a few events. There are 4 parts in part A and then a slightly non-standard question in part B. But let's look at part A first. We should all be very familiar with the concepts being asked in part A. So let's take a look before we answer the question. Probability of landing on blue is 0.11. And we are asked in part A1, the probability that the spinner lands on blue for the first time on the 6th spin. We should all recognize straight away that this is asking us to look at the geometric distribution. The geometric distribution effectively look at the number of attempts needed for the first success to come up. Here, we are asked, what if the first success comes up on the 6th spin? It's quite straightforward, and let's define our random variable. We're going to call this random variable x. We're going to call this the number of attempts needed for blue to land for the first time. Part A1 is effectively asking us, what's the probability that x equals 6? What's the probability that it takes us 6 attempts to get blue for the first time? Which means that we have 5 failures, so 1 minus 0.11 for 5 times, and success 0.11 for the final time. Working this out, it gives us 0.061425. Rounding that to 3 significant figures is 0.0614. So that's our answer to part A1. What about part B? Part B is asking us, what's the probability that a spinner lands on blue for the first time before the 6th spin? Now, what's the inequality? So if x is the number of attempts needed for blue to land for the first time, in words, what does it actually mean? So we could have blue for the first time, so that's x equals 1 for the first spin. If we could have blue for the first time, the second spin equals 2, for the third spin, for the fourth spin, for the fifth spin, and because the question is saying that it wants blue to land for the first time before the 6th spin. So these are the probabilities that we are interested in. So either x equals 1, 2, 3, 4, and 5. Now, you can work these probabilities out just like I did in part A. So because I've worked out in part A what probability of x equals 6 is. So very similarly, you could work out what the probability of x equals 1, x equals 2, etc. Because we know that in a geometric distribution, and that's given in your formula booklet, probability to get a first success in x number of attempts is simply 1 minus p to the power x minus 1 times p. So that's how we work that out, and we can sum that up. For example, we can write that as 0.11 plus 0.89 times 0.11 plus plus 0.89 to the 4 times 0.11. So we could work this out. Alternatively, from this expression, we could write this as probability of x less than or equal to 5. And this is the same as 1 minus probability of x greater than 5. So in order for us to have a success event in the first 5 spins, that probability is the same as 1 minus probability of not having any success events in the first 5 spins. So what's the probability of not having any success events in the first 5 spins? Is simply failure, so 0.89 to the power 5, so 5 times failure. And to work out this probability, we get 0.44159 to 3 significant figures is 0.442. So that's our answer to part A2. Part 3 of A is a little bit simpler. It is to do with a binomial distribution. The question asked us, what's the probability that the spinner lands on blue exactly 4 times during the first 6 spins? So let's call this random variable y. So y is the number of blues in first 6 spins. And based on the question, y follows a binomial distribution with 6 attempts, because we've been told that, well, we're spinning the spinner 6 times, and the probability of success to get a blue is 0.11. And I'm interested in probability of y equals 4. So what's the probability that, looking back at the question, we get blue exactly 4 times in the first 6 spins? So this is how we write out the probability. We can use the calculator, plugging in the variables, but we can also write out the probability by first principles. So basically 2 failures and 4 successes out of the 6 events. This gives us 0.00173957, rounding to 3 significant figures. That gives us to 0.000174. So that's our answer to part A3. Now let's look at part 4 of A. It's asking us to find the probability that the spinner lands on blue for the 4th time on or before the 6th spin. So I've got 6 spins, so 1, 2, 3, 4, 5, 6 spins. I'm interested in the probability that I get 4 blues on or before the 6th spin. So I could have blue, blue, blue. I could have blue there, and then it doesn't matter what it is. Or I could have blue, 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 not blue, and I'm going to call not blue N, and then I could have blue there, and then it doesn't matter what it is. Or I could have blue, 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 not blue, not blue, blue. So I could have all of these combinations, but then to draw all of these combinations out, it's going to take us a while. Let's see what distribution we could be using and what notation we could be using as well. I'm going to name a new random variable. I'm going to call this F for 4 times. There are actually 2 different distributions that we could be using. I'm going to start with the negative binomial distribution first, which you might recognize. I'm going to call this variable F. So F is the number of attempts needed for 4 blues. I use the negative binomial distribution because the number of success is fixed. So here it's fixed at 4. And I'm interested in the total number of events to be 4, 5, or 6. Because the question is telling us I want that 4th time blue to happen on or before the 6th spin. So in mathematical notation, the probability I'm interested in is probability of F less than or equal to 6. Effectively, that's probability of F equals 4, because it needs to happen at least 4 times, or probability of F equals 5. 5 spins, I get 4 blues, or probability of F equals 6. You may remember the formula for the probability distribution, but if not, we can always consult formula booklet. This is the formula booklet, and we're in the statistics section. Let's look at negative binomial distribution. So this is a negative binomial distribution, and this is the probability for x equals small x. So let's bring that back to our question. Now, this is what we got from the formula book. P of x equals little x for negative binomial distribution. And then we are going to use this formula. Now, we've got this formula here, but what's our R and what's our P? R, in this case, is the number of successes, therefore equals 4. What about P? P equals 0.11 because that's our probability of success. Now, X will depend on what we have in the probability formula. So it could be 4, could be 5, could be 6. Therefore, I'm just going to write the next line in this equation. Probability of F equals 4. What is X? X here is 4. So X minus 1 is 4 minus 1. What's R? R is also 4. So R minus 1 is 4 minus 1 as well. Now, what's P to the power R? P is 0.11. R is 4. So that's 0.11 to the power 4. What's 1 minus P? 1 minus P is 0.89. X minus R is 4 minus 4. I've written this out, but you should be able to work out that, well, if I want 4 blues in the first 4 attempts, this is simply the same as 0.11 to the power 4 because I just want 0.11, which is the probability success 4 times. What about 4 blues in the first 5 attempts? That is simply replacing x equals 5. So 5 minus 1, 4 minus 1, 0.11, again to the power 4 because there are 4 successes, and then 0.89 of 5 minus 4, which is 1. I'm just going to write that out for clarity. And then what is probability of F equals 6? So we want in the first 6 attempts, there are 4 blues, but I want the 6th attempt to be a blue as well. So that is 6 minus 1, 4 minus 1, 0.11 to the 4, 0.89 to the 2. That gives us 0.0018273. Rounding to 3 significant figures, that's 0.00183. Well, that's one way of dealing with it, using the distribution, the negative binomial distribution. The negative binomial distribution is actually very closely related to the binomial distribution, and this is one distribution that we could be using as well. Now I'm going to define another variable. I'm going to call this g here because I used f earlier. And you'll see what I'm going to be doing here. I'm going to use the binomial distribution, and I say there are 6 events with 0.11 probability of success. Now, what is the probability equation that I want to be working out here? If I want to know the probability that the spinner lands on blue for the 4th time on or before the 6th spin, we have defined that G follows the binomial distribution with 6 events and 0.11 probability of success. So basically, G is the number of blues in 6 spins. Now, if I spin the spinner 6 times and I want the spinner to land on blue for the 4th time on or before the 6th spin, it means that when it gets to the 6th spin, I need at least 4 blues to have appeared. So let me say that again. If I'm spinning the spinner 6 times and I want blue to have landed for the 4th time on or before the 6th spin, then I want to have seen blue having landed 4 times or more. So the probability that we need to be seeing is V greater than or equal to 4. So I want blue to have appeared 4 times, 5 times, or 6 times in the first 6 spins. This might be an easier probability for you to work out. You can plug this into the calculator, or you can simply write, okay, G equals 4 plus G equals 5 plus probability of G equals 6. Again, we could plug this into the calculator with n equals 6, probability of success equals 0.11, but we can simply work that out as well. So using the formula for the probability for binomial distributions. That is that. And then G equals 5 is 6 choose 5, 0.11, 5 successes, 1 failure. And then finally, it's just 6 successes. So that actually gives us exactly the same answer, 0.00183, which is exactly the same as what we got using the negative binomial distribution. So we can see that there's a relationship between using the negative binomial distribution and the binomial distribution. Now let's look at part B of the question. It might be slightly non-standard, but it's certainly something that we could do. I've copied here the first paragraph from the question. The new part of the question starts with Zach and Izana play the game. They take turns to spin a spinner. The winner is the first one to have the spinner land on blue. Izana spins the spinner first. In part B, we are asked to show that the probability of Zach winning is 0.471 to 3 significant figures. So how do we go about tackling this question? Maybe we can draw that out first. So we have Izana spinning, Zach spinning, Izana spinning, Zach spinning, Izana spinning, Zach spinning, and so on. Now, Zach wins if we have, so I'm going to call blue, so B, blue lands, and then N, non-blue, B doesn't land, okay? Define my random variables. So Zach could win if, let's say, in terms of the event, I could have non-blue, blue, or I could have not blue, not blue, not blue, blue, or I could have not blue, not blue, not blue, not blue, not blue, blue, because I want Zach to win, and Zach is here. Zach is there. Zach is there. And if I carry on, I'll see a pattern there. So let's do that one more time. So Zach. So that's not blue, not blue, not blue, not blue, not blue, not blue, Not blue for Izana, but blue for Zach. So that is possible as well. So that's a winning event for Zach because no blues are appearing for the first 7 times, and then for the 8th time, I want a blue to appear. So on and so forth. What I want to find out is simply all these probabilities added together. So there is a probability here, let's call it P1, probability here, probability there, probability there. So all these events added together, and then P5 all the way. So blue will be there. The probability that Zach wins equals P1 plus P2 plus P3 plus P4 all the way. Okay? Now, how do I work out all these probabilities? Why don't we take a look at the first one first? What is P1? P1 is a non-blue event first, so an N first, and then a blue. So P1 is simply 0.89 times 0.11. What about P2? It looks like I've got 3 non-blue events and 1 blue event. So that's 0.89 to the 3 times 0.11. What about P3? I've got 5 non-blue events and 1 blue event. Therefore, I have 5 failures and then 1 success. And are you seeing the pattern there now? So P4 is 7 non-blue events and 1 blue event. So it's 0.897 times 0.11. So the probability of Zach winning, just bring that out there, probability of Zach winning is 0.89 times 0.11 plus 0.89 cubed times 0.11 plus 0.89 to the 5, 0.11 plus 0.89 to the 7 times 0.11, etc., etc. And you see the pattern there, 0.89 times 9, 0.1, etc. Now, we can't just finish the answer like this. You might recall how we sum up geometric series. There's a formula for it, and if you don't remember the formula, again, you can refer to the formula book. In part 2 of the formula book, we can actually see formula for the infinite geometric series. So A is the first term, and R is the common ratio, where the common ratio is less than 1. So let's see whether we can use this. Here, the formula for the sum of a geometric series from the formula booklet. Again, A is the first term and R is the common ratio. So let's take a look. Well, we can see that the first term is simply 0.89 times 0.11. But more importantly, we need to check that the common ratio is less than 1, or the absolute value of that is less than 1. What is the common ratio in this series? So that's the first term. 0.89 in the first term, 0.89 to the 3 in the second term, 0.89 to the 5 in the third term, 0.89 to the 7 in the fourth term. So we can say that the common ratio R is 0.89 squared. Therefore, using the formula from the formula booklet, we can say that the sum of this geometric series is the first term, which is 0.89 times 0.11, all over 1 minus R, and R is 0.89 squared. Working all of this out, we get 0.47089 ... and great, that is what we have from the question, which is to show that Zach has a probability of winning of 0.471 to 3 significant figures. So what does it tell us about the game? It tells us that Zach could win in about 47% of the time, and Izana could win in about 1 minus that, which is about 53% of the time. So even though they're spinning the same spinners, Izana actually has a higher probability of winning because she's going first.